Good morning. Let us study today Enzyme Kinetics Part 2. We have already studied the mechanism of enzyme catalyzed biochemical reactions. I have written here also the mechanism. Based on the mechanism, using steady state approximation, Michaelis-Menton equation is derived. This is very important equation. Every year, at least one or two questions asked in GATE, Csir, JAM. Okay. So it is very important. Please remember this Michaelis-Menton equation. R equal to K2 enzyme concentration, initial enzyme concentration, substrate concentration divided by Km plus substrate concentration, where Km is Michaelis-Menton constant. Michaelis constant. It is equal to K minus 1 K inverse plus K2 divided by K1. K1, K inverse I have shown here. What is K1, K minus 1, K2. Okay. This Michaelis-Menton equation can be rewritten. This Michaelis-Menton equation can be rewritten in this form, Vmax, where Vmax equal to K2 concentration of initial concentration of enzyme divided by Km plus substrate concentration, where Vmax is the maximum rate of the enzyme catalyzed reaction. Okay. Now, this is a fundamental equation. Many problems were asked, as I said. There are three cases. Let us consider one by one. When substrate concentration is very much greater. See. Therefore, then, when substrate concentration, this will be negligible. When substrate concentration is greater, this is very large. Therefore, Km is negligible. Therefore, R equal to Vmax. The rate of the reaction, the rate of the enzyme catalyzed reaction is independent of substrate concentration. Therefore, zero order. Yeah, on plotting this equation, on plotting Michaelis-Menton equation, we obtain Michaelis-Menton plot. This is called the Michaelis-Menton plot. When R is plotted against substrate concentration, with increasing substrate concentration, this graph is obtained. For example, high concentration, see substrate concentration is high. Beyond A, it becomes a straight line. Beyond A, however, you increase the substrate concentration, there is no change in the rate. The rate is independent of, therefore, along the line AB, the rate of the reaction is independent of substrate concentration. The rate does not depend on the substrate concentration. However, you increase the substrate concentration, the rate becomes constant. That is the maximum rate. This is the maximum rate attained. Okay. Now, the second case is that Km is greater than substrate concentration. When Km is greater, therefore, your substrate concentration is small. Therefore, R by, it is written as Vmax substrate concentration divided by Km. Now, the rate of OA line, the OA curve obeys this case 2, this equation. It corresponds to first order. Therefore, OA curve corresponds to first order kinetics, enzyme kinetics. Therefore, the rate along the curve OA, the rate of the reaction depends on the rate varies. You see, the rate increases with increasing substrate concentration. Therefore, the rate of the reaction depends on the first power of the substrate concentration. Therefore, it is a first order kinetics. It will be asked several times. The questions were asked. The third case is Km equal to substrate concentration. Now, Km equal to substrate concentration, therefore, you put substrate concentration to substrate concentration, therefore, R equal to Vmax by 2. At this condition, for example, in problem, they will ask, when Michaelis-Menton constant is equal to substrate concentration, calculate the rate of the reaction, calculate the Vmax. So, this formula is used. Okay. Using this Michaelis-Menton equation, a straight line is not obtained. Therefore, it is very difficult to determine Vmax and Km, Vmax and the Michaelis-Menton constant from the Michaelis-Menton equation plot. Okay. Therefore, there are two other methods. Lineweaver-Burk plot and Eadie-Hofstee plots were used. They simply converted the Michaelis. They used the Michaelis-Menton. This is the fundamental equation. You please remember. They converted the Michaelis-Menton equation by rearranging the equation into a straight line equation, so that a straight line plot is obtained. See, so that a straight line, from the straight line plot, Km and Vmax are easily, accurately, readily determined. Okay, from the straight line plot, they are accurately, readily determined. How they converted? For example, let us see first the Lineweaver-Burk plot. In this, they inverted the equation. Michaelis-Menton equation is inverted so that it is converted, so that it becomes a straight line equation. You see, 1 by r. Now this goes here, Km plus S divided by Vmax. Vmax here, Vmax substrate concentration. Therefore, you divide Km by Vmax substrate concentration and plus 1 by this will get cancelled, plus 1 by Vmax. This equation is called 2. Okay. Now this is a straight line equation. This is y. This is x. This is m. This is c. Okay. This is a straight line equation. A graph is plotted by them called Lineweaver-Burk plot between 1 by r and 1 by substrate concentration. 1 by r and 1 by substrate concentration. Here, r is plotted against substrate concentration. You remember, 1 by r is plotted against. Now, a straight line is obtained with the slope. This is the slope, with the slope equal to Km by Vmax, and this is 1 by Vmax is the y-axis intercept. This is the y-axis intercept. From the y-axis intercept, on taking reciprocal, Vmax is obtained. Once Vmax is obtained, you substitute in the slope, then you will get the Km value, Michaelis-Menton constant. In a similar manner, Eadie and Hofstee, they also rearranged the Michaelis-Menton equation by inverting the Michaelis-Menton equation, one equation they inverted, and multiplied. They inverted the Michaelis-Menton equation is first inverted and then multiplied by Vmax, or you simply multiply the equation 2 by Vmax. Okay, both are same. Now Vmax multiply Vmax by R equal to Vmax will get cancelled. Therefore, Km by substrate concentration, Vmax plus 1. Therefore, on cross multiplying, Vmax equal to R Km, R by substrate concentration, Km plus R. Now you take out R. Therefore, R equal to minus this side, bring this side. Therefore, Km or substrate concentration plus Vmax. This is now a straight line equation. By rearranging the Michaelis-Menton equation, it is now converted into a straight line equation. A graph is plotted y equal to mx plus c, y is equal to r, m equal to minus km, okay, c equal to Vmax. A graph is plotted between r and 1 by substrate concentration. Okay. Now a straight line is obtained with the negative slope. This is positive slope. This is negative slope. From the slope Km minus Km value is obtained. From the, and this is the y-axis intercept. C is called y-axis intercept. This is Vmax. From the y-axis intercept, from the graph, from the straight line plot, Vmax is obtained, and from the x-axis intercept, what is called, sometimes it may be asked, they will give in problems, they will give x-axis intercept. How x-axis intercept is obtained? See, when x-axis intercept means y, there is no y value here, y equal to 0. Therefore, y equal to 0, mx plus c. Similarly, you put r equal to 0. Here, r equal to 0 here. Okay. Therefore, r equal to 0 in this equation, r equal to 0, then Vmax equal to Am r by s. Therefore, r by s. This is r by s. X-axis intercept equal to Vmax divided by k. Vmax divided by k. So, from the plot, the x-axis intercept and y-axis intercept and slopes are obtained. A problem was asked in Csir 2014. I will just go through this. Thank you for watching.